Okay, now, after doing that, we have to talk about two things that happen when we talk about drag. One is when time is small, and two is when time is large. So when time is small, and when time is large. So when t is very, very small, that means right after something starts to fall, may I write e to the minus bt over m as approximately 1 minus bt over m from the expansion e to the power x. We talked about that. When t is small, I can do that. When t is large, that means after a long time, after 0, is e to the minus infinity is 0. So then, does my equation ghost become mg over b, 1 minus 1 plus bt over m? Do ones go away? Am I left with mg over b times bt over m? So v as a function of time is just gt. Yeah, after all of this, we came back to the equation of motion again. Isn't that fascinating? Which should be very comforting, right? It's like it doesn't matter. Physics doesn't change no matter what you do to it. Okay, so now what happens to the ghost equation for when time is large? Vt becomes mg over b. And we call this terminal velocity, because at this point, if you plug this value in equation candy, this one, that looks like candy, right? Okay. So if you plug this value back in this equation, what will you get? So it was A, remember this, I'm going to rewrite this again. A equals G minus D over M, and this is G minus BV over M, or that could be G minus B mg over B divided by M. This gets canceled, this gets canceled, G minus G is 0. So at terminal velocities, things stop accelerating.
Hey, I knew that.
And that's why squirrels are so good, right? They reach terminal velocity very quickly. That's why they don't die when they fall off of trees. I mean, it doesn't mean that they stop falling. It just means that they stop accelerating. They have a constant velocity of fall. That is why we need parachutes, right? Humans.